Okay, hi everyone, welcome back to this video series on data centers, IPv6 addressing. People refer to IPv6 as the next generation internet protocol, and it was originally created as the answer to IPv4's inevitable looming address exhaustion crisis. Though you've probably heard a thing or two about IPv6 already, it has been improved even further in the quest to bring us flexibility, efficiency and capability and optimized functionality that can truly meet our ever-increasing needs. The capacity of its predecessor IPv4 pales in comparison, and that's the reason it will eventually fade into history completely. IPv6 header and address structure has been completely overhauled, and many of the features that were basically just afterthoughts and add-ons in IPv4 are now included as full-blown standards in IPv6. It's seriously well equipped, poised and ready to manage the mind-blowing demands of the internet to come. Why do we need IPv6? Well, the short answer is because we need to communicate, and our current system isn't really cutting it anymore. Kind of like how the Pony Express can't compete with airmail. Just look at how much time and effort we've invested in coming up with slick new ways to conserve bandwidth and IP addresses. We've even come up with variable length subnet masks, VLSMs, in our struggle to overcome the worsening address drought. It's really the number of people and devices that connect to networks increases each and every day. That's not a bad thing at all. We're finding new and exciting ways to communicate and to more people all of the time, and that's a good thing. In fact, it's a basic human need, but the forecast isn't exactly blue skies and sunshine, because IP version 4, upon which our ability to communicate is presently dependent, is going to run out of addresses for us to use. IPv4 has only about 4.3 billion addresses available in theory. We know we don't even get to use most of these. Sure, the use of classless interdomain routing, CIDR, and network address translation have helped to extend the inevitable dearth of addresses, but we will run out of them, and it's going to happen within a few years. China is barely online, and we know there's a huge population of people and corporations there that surely want to be. There are lots of reports to give us all kinds of numbers, but all you really need to think about to convince yourself that I'm not just being alarmist, in fact, that there are about 6.8 billion people in the world today, and it is estimated that just over 10% of the population is connected to the internet. That statistic is basically screaming to us the ugly truth that's based on IPv4's capacity. Every person can't even have a computer, let alone all the other IP devices we use with them. I have more than one computer, and it's pretty likely you do too. And I'm not even including the mix of phones, laptops, game consoles, fax machines, routers, switches, and mother lobe of other devices we use every day. So I think I've made it pretty clear, and we've got to do something before we run out of addresses and lose the ability to connect with each other as we know it, and that something just happens to be implementing IPv6. The benefits and uses of IPv6. So what's fabulous about IPv6? It is really the answer to our coming dilemma. Is it really worth it to upgrade from IPv4? All good questions. You may even think of a few more. Of course, there's going to be a group of people with time-tested and well-known resistance to change syndrome, but don't listen to them. If we had done that a few years ago, we'd all still be waiting weeks, even months, for our mail to arrive via horseback. Instead, just know that the answer is a resounding yes. Not only does IPv6 give us lots of addresses, 3.4n 1038 equals definitely enough, but there are many other features built into this version that make it well worth the cost, time and effort required to mitigate it. Here are the 3 benefits of migrating from IPv4 to IPv6. IPv6 eliminates the requirements for NAT. IPv6 includes enough addresses to allocate more than 4 billion IP addresses to every person on Earth. Hosts can be assigned with an IP address without DHCP. Today's networks, as well as the internet, have a ton of unforeseen requirements that simply were not considerations when IPv4 was created. We've tried to compensate with a collection of add-ons that can actually make implementing them more difficult than they would be if they were required by standard. By default, IPv6 has improved upon and included many of these features as standard and mandatory. One of the suite new standards is IPsec, a feature that provides end-to-end security. Another little beauty is known as mobility, and as its name suggests, it allows a device to roam from one network to another without dropping connections. But it's the efficiency features that are really going to rock the house. For starters, the headers in an IPv6 packet have half the fields, and they have aligned to 64 bits, which gives us some seriously souped up processing speed compared to IPv4. Lookups happen at light speed. Most of the information that's used to be bound into IPv4 header was taken out, and now you can choose to put it or parts of it back into the header in the form of optional extension headers that flow from basic header fields. And of course, there's that whole new universe of addresses, 3.4N 1038, enough for 4 billion addresses to be signed to each person on Earth. We talked about already, but where did we get them? Did the Chris Angel mind freak dude just show up and blammo? I mean, a huge proliferation of addresses had to come from somewhere. Well, it just so happens IPv6 gives us a substantially larger address space, meaning the address is a whole lot bigger, 4 times bigger as a matter of fact, and IPv6 address space is actually 128 bits in length. No worries, I'm going to break down the address piece by piece and show you exactly what it looks like. Coming up in the section IPv6 addressing and expressions. For now, let me just say that all that additional room permits more levels of hierarchy inside the address space and a more flexible addressing architecture. It also makes routing much more efficient and scalable because the addresses can be aggregated a lot more efficiently, and IPv6 also allows multiple addresses from hosts and networks. This is especially important for enterprises joining for enhanced availability. Plus, the new version of IP now includes expanded use of multicast communication, one device sending host or to select group, which will also join in to boost efficiency on networks because communications will be more specific. IPv4 uses broadcast quite prolifically, causing a bunch of problems, the worst of which, of course, the dreaded broadcast storm, an uncontrolled deluge of forwarded broadcast traffic that can bring an entire network to its knees and devour every last bit of bandwidth. Another nasty thing about broadcast traffic is that it interrupts each and every device on the network when a broadcast is sent out. Every machine has to stop what it's doing and respond to the traffic, whether the broadcast is meant for it or not. But smile everyone, there is no such thing as a broadcast in IPv6 because it uses multicast traffic instead. And there are 2 types of communication as well. Unicast, which is the same as it is IPv4, and a new type called Anycast. Anycast communication allows the same address to be placed on more than one device, so that when traffic is sent to the device service addressed in this way, it is routed to the nearest host that shares the same address. This is referred to as one-to-nearest. This is just the beginning. We'll get more into the various types of communication in the section called address types. IPv6 addressing and expressions. Just as understanding how IP addresses are structured and used is critical with IPv4 addressing. It's also vital when it comes to IPv6. You've already read about the fact that it's 128 bits, and IPv6 address space is much larger than an IP version 4 address. Because of that, as well as new types of addresses can be used, you've probably guessed that IPv6 will become more complicated to manage, but no worries. As I said, I'll break down the basics and just show you what the address looks like and how you can write it and what many of us common uses are. It's going to be a little weird in fact, but before you know it, so let's take a look at figure 5.3, which is a sample IP address broken down into sections. So 201000DB8:00000000:1234:56 AB global prefix subnet interface ID. As you can now see, the address space is much larger, but what else is different? Well, first notice that it has 8 groups of numbers instead of 4, and also that these groups are separated by colons instead of periods. And hey, wait a second, there are letters in that address. Yep, the address is expressed in hexadecimal just as a MAC address is. So you could say the address has 8 6-bit hexadecimal delimited blocks. IPv6 addresses are called 128-bit delimited hexadecimal. That's really quite a mouthful, and you've probably haven't even tried to say that address in figure 5.3 out loud yet. One other thing I want to point out is for when you set up your test network to play with IPv6, because you're going to want to do that when you use a web browser to make a HTTP connection to an IPv6 device. You have to type the address into the browser with brackets around the literal address. Why? Well, a colon is already being used by the browsers for specifying a port number. So basically, if you don't enclose the address in brackets, the browser will have no way to identify the information. Here's an example of how it looks. HTTP bracket 2001:0 DB8:0003C4D:0000001234:56 AB close bracket default.html. Shortened expression. The good news is that there are a few tricks to help rescue us when writing these monster addresses. For one thing, you can actually leave out parts of the address to abbreviate it, but to get away with doing so, you have to follow a couple of rules. First, you can drop any leading zeros in each of the individual blocks. After you do that, the sample address from earlier would then look like this: 2001:DB8:00:3C4D:0:0:1234:56 AB. That's a definite improvement. At least we don't have to write all those extra zeros. But what about the whole blocks that don't have anything in them except zeros? Well, we kind of lose to at least some of them. Again, referring to our sample address, we can remove the 2 consecutive blocks of zeros by replacing them with a double colon like this: 2001:DB8:3C4D:12:1234:56 AB. We replace the blocks of zeros with a double colon. The rule you have to follow to get away with this is that you can replace only the contiguous block of such zeros in an address. So if my address has 4 blocks of zeros and each of them were separated, I don't just get to replace them. all. Remember, the rule is that you can replace only one contiguous block with a double colon. Check out this example. 2001 colon 0000 colon 0000 colon 0012 colon 0000 colon 0000 colon 1234 colon 56AB. And just that you know, you can't do this 2001 colon 12 colon 1234 colon 56AB. Instead, this is the best that you can do. 2001 double colon 12 colon 0 colon 0 colon 1234 colon 56AB. The reason the preceding example is our best shot is that if we remove two sets of zeros, the device looking at the address will have no way of knowing where the zeros go back in. Basically, the router would look at the incorrect address and say, well, do I place 2 blocks into the first set of double colons and 2 into the second set, or do I place 3 blocks into the first set and 1 block into the second set, and so on. And would it go because the information the router needs just isn't there? Address types. We're all familiar with IPv4 unicast broadcast and multicast addresses that basically define who, or at least how many other devices we're talking to. But as I mentioned, IPv6 modifies that trio and introduces the Anycast broadcast as we know them have been eliminated in IPv6 because of their cumbersome inefficiency. So let's find out what each of these types of IPv6 addressing and communication methods do for us. Unicast packets addressed to a unicast address are delivered to a single interface. There are a few different types of unicast addresses, but we don't need to get into that here. Global unicast address. These are your typical publicly routable addresses, and they're the same as they are in IPv4. Global addresses start at 2000 colon /3. Link local address. These are like the private addresses in IPv4 in that they're not meant to be routed, and they start with FE80 double colon /10. Think of them as a handy tool that gives you the ability to throw a temporary LAN together for meetings, or to create a small LAN that's not going to be routed but still needs to share and access files and services locally. Unique local addresses, RFC 4193. These addresses are also intended for non-routing purposes over the internet, but they are nearly globally unique, so it's unlikely you'll ever have one of them overlap. Unique local addresses were designed to replace site local addresses, so they're basically do almost exactly what IPv4 private addresses do. Allow communication throughout a site while being routable to multiple networks. Site local addresses were denounced as of September 2004. ULAs contain a 40-bit random number in the prefix and are found in the IPv6 address block of FC00 7. They are not routable over the internet. Multicast, again, same as IPv4, packets addressed to a multicast address are delivered to all interfaces tuned into the multicast address. Sometimes people call them one-to-many addresses. It's really easy to spot a multicast address in IPv6 because they always start with FF. Anycast, like multicast addresses, an Anycast address identifies a single unicast address on multiple interfaces, but there's a big difference. The Anycast packet is delivered to only one device, actually to the closest one it finds defined in terms of routing distance, and again the address space is special because you can apply a single address to more than one interface. These are referred to as 1 to nearest addresses. Summary. If you've made it this far and understood everything the first time through, you should be proud of yourself. We've really covered a lot of ground in this chapter, but understand that the information in this chapter is key to being able to navigate through the rest of this book. Even if you didn't get a complete understanding first time around, don't stress. It really wouldn't hurt you to read this chapter more than once. There's still a lot of ground to cover, so make sure you've got it all down and get ready for more. What we're doing is building a foundation, and you want a strong foundation right after you've learned about the DoD model, the layers, associated protocols. You learned about the so important IP addressing. I discuss in details the difference between each class of address and how to find a network address, broadcast address, and valid host range, which is critical information to understanding before going on to chapter 6. The chapter ended with an introduction to IPv6. I discussed the reason for IPv6, the 128-bit colon delimited hexadecimal address, and the different types of addresses. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.